We're continuing to look at elections based on preference ballots, and we're looking at various methods for resolving those elections. We've already looked at the plurality method, and now let's turn to the method of pairwise comparisons. Now, to begin, let me tell you about something called the Condorcet criterion. That's named for the person you're looking at right now, a Frenchman from the 18th century, the Marquis de Condorcet. And here's what he said. If one candidate is preferred to each other candidate in a head-to-head comparison, then that candidate should win. This is called the Condorcet criterion. Here's how you would use it in practice. Compare each pair of candidates. If one candidate is preferred to each other candidate in a head-to-head comparison, then that candidate is declared the winner. We're going to call that candidate the Condorcet winner. Now, to illustrate that, let me give you an example. This is an example that's taken from a Wikipedia article. It's just a made-up example. We're going to imagine that Tennessee is having an election to decide the location of its capital. This isn't really true. Actually, the capital of Tennessee is Nashville, and nobody is challenging that. But let's just suppose that we're going to have an election, and that the four candidates are the cities as shown here on the map: Memphis, Nashville, Knoxville, and Chattanooga, whose name is cut off towards the bottom of that picture. Memphis is in the very southwest corner, Nashville towards the center, Knoxville very far to the east in the mountains, and Chattanooga almost in Georgia in the southeast of Tennessee. All right, this is just a made-up example, and the numbers here are also made up. We're going to suppose that only the following preferences are expressed by the voters. First of all, there's some voters that live close to Memphis, which remember is in the west, and their preference, of course, is to have Memphis as the capital. If they can't have that, then they'll take the next closest, which is Nashville. After that, their choice would be Chattanooga, and finally, their least favorite choice is Knoxville. Looking at the voters close to Nashville, and we assume that's 26% of the voters, their first choice is Nashville. If they can't have Nashville, then they want Chattanooga, and then Knoxville, and then Memphis. And the other voters are as shown. You'll notice that these numbers add up to 100%. So all the voters have been represented. Each one of the voters has cast one of these four types of ballots. Now, let's do a comparison of two of those cities. Just arbitrarily, let's start with Memphis and Nashville. So I'm showing you again the same preference schedule up above, but now I'm graying out the other cities because I want to concentrate on the relative positions of Memphis and Nashville. So if you look at the 42% of voters who are close to Memphis, the ones that are indicated here, of course they prefer Memphis to Nashville. So 42% of the voters prefer Memphis to Nashville. Then we have these 26% of the voters. They live close to Nashville, and their preference is for Nashville over Memphis. And actually is the same as the true of this 15% when we're just comparing Nashville and Memphis. Now, neither one of them expressed any great desire, but if you're just comparing the two, you'll notice Nashville comes out ahead, and the same thing is true for the 17% of the voters close to Knoxville. They prefer Nashville to Memphis. So now, if we consider all the voters, but only consider these two cities of Memphis and Nashville, you see that Memphis was preferred on 42% of the ballots, and Nashville was preferred on 58% of the ballots. So in that head-to-head comparison, the winner is Nashville, 58% to 42%. Well, one can do the same thing with any other pair of candidates, and let me just show you all the other results. Let's do one more of these just to show how it's done. So let's consider, for example, Nashville versus Knoxville, this one right here, and how we came up with the 68 and 32%. Well, again, I just want to look at the two cities that have been named, Nashville, Knoxville. Let me circle them everywhere that they occur. All right, and we're going to ignore all the others. It's as if these others are crossed out. I won't cross them all out completely, but just look at the cities that have been circled. So here Nashville is preferred. Here Nashville is preferred. Here Knoxville is preferred, and here Knoxville is preferred. So what did Nashville do? Nashville got these 42%. And also these 26%, that's a total of 68%, whereas the remaining ones, the 15 plus 17%, which is 32%, prefer Knoxville. So that's how I came up with the numbers you see down below, the 68% and the 32%. So you can see Nashville is preferred to Knoxville, and the winner of that head-to-head comparison is Nashville. So you can do this for all possible pairs. You might have to stop and think, well, how many pairs do I need to compare? If there are 4 candidates, it turns out you need to do 6 head-to-head comparisons. Now, some of those don't involve Nashville at all, but 3 of those did involve Nashville, and you want to note the following. Nashville 1 here, Nashville 1 here, Nashville 1 here. Every time that Nashville was looked at in a head-to-head comparison here, it won. And therefore, this tells us that we have a Condorcet winner. Let me just write CW for Condorcet winner. Nashville was the Condorcet winner. When you're doing this method of pairwise comparisons, you somehow need to keep track of all the pairwise comparisons that you need to do. And a nice way to do that, and a nice way to record the information, is to use an idea from earlier in the course, namely to use a complete graph. After all, that's what we want. We want to consider each of the candidates as vertices, and each comparison that we want to do is represented by an edge. Now, we can orient those edges according to who wins the head-to-head comparison. So if you look, for example, you notice that all the edges coming into Nashville have been oriented coming into Nashville. That is to say, the arrows are pointing inward, and that reflects the fact that Nashville is a Condorcet winner. That's how you can look at this kind of graph and see that you've got a Condorcet winner. As you can see, Nashville won all 3 head-to-head comparisons that it was involved in. Chattanooga won 2 of the head-to-head comparisons it was involved in. Knoxville won 1, and Memphis didn't win any head-to-head comparisons at all. So that's how you can discover a Condorcet winner. Let's note that the number of comparisons you need to make is the number of edges in the complete graph. So in the example that we just did, we had 4 candidates, and therefore we had the complete graph on 4 vertices, which has 6 edges. In general, how many comparisons will you have to do? Well, that's equivalent to asking the question, if I have a complete graph, how many edges do I have? And the answer depends on the number of vertices. If you have n vertices, then you can easily work out this formula. For the number of edges, it's 1/2 times n minus 1. For example, if n is equal to 2, this will give you the number 6 that we already said. If n is 5, what will be the number of edges? Well, it will be 1/2 times 5 times 4, which is 10, and you might remember when we were studying graph theory, that indeed is the number of edges in the complete graph on 5 vertices, and that's therefore the number of head-to-head comparisons that you need to do when you use this method. Now, as explained thus far, we don't know what to do if there's not a Condorcet winner, and often there isn't a Condorcet winner. That is to say, every candidate may lose a head-to-head comparison. You can still, however, use this idea in a different way. You can still use head-to-head comparisons to resolve the election. What you do is you declare the winner to be the candidate who wins more head-to-head comparisons than any other. If you do this, this is what we call the method of pairwise comparisons. So I'm giving you an example here. I'm not even showing you the votes. I'm just showing you this complete graph. I'm supposing that there are 5 candidates and their names are simply A, B, C, D, and E, and there is no Condorcet winner. You see, if there were a Condorcet winner, we would see a vertex at which all the edges were directed inward, and that's not true. On the other hand, one can see how many head-to-head comparisons each candidate has won. For example, if we take candidate B, that candidate has only won a single head-to-head comparison. Candidate A has won 2 head-to-head comparisons, but the candidate that has done the best is candidate E, who has won 3 head-to-head comparisons, and therefore in this method E is declared to be the winner. Now there's still a problem, and the problem is that there still may be a tie. That is to say, there may be several candidates, 2 or more candidates, who all win the same number of head-to-head comparisons. So in this case, one needs to invoke some sort of tie-breaking rule. In the recitation, we're going to have an example like that, and I will propose a rule for you to use. Now, what are the defects of this method? Well, the first is, as you think about it, it involves many comparisons. Suppose you have 7 candidates. How many comparisons will you need to do? It turns out there were 21 different head-to-head comparisons to be worked out. That's a lot of work. A second defect, as we've already seen, is that you may need a special tie-breaking rule. That is to say, there won't be a candidate that wins for having won the most head-to-head comparisons because there will be some sort of a tie. And another defect which we haven't seen and we're not going to explore very much is this one, which will, I hope, seem rather disturbing. It turns out if one candidate withdraws from the race and you recompute the head-to-head comparisons, the winner may change. That seems a rather undesirable feature, don't you think? Let me show you a few other examples here. In this example, I'm supposing there are 4 candidates, A, B, C, D, with the preference schedule as shown below. Now let's actually work things out. Now I won't work this out completely, but let us simply look at the pairwise comparisons that involve candidate C. So there's 3 that I need to look at here. First of all, let's look at C versus A. And as we do that, well, we see in those first 15 ballots, A is preferred to C, but in the other remaining 22, C is preferred. So that's 22 versus 15, and the winner there is C. Let's do C versus B. So in the first 15, C is preferred, and also in the next 12, C is preferred, and finally in the last 10, B is preferred. So that's 27 to 10 in favor of C. And then finally, let's do C versus D. So on the first 15, C is preferred, also on the last 10. So that's a total of 25. And D is preferred over C in just 12. And what we're seeing here is that C has won all the pairwise comparisons. The comparison with A, the comparison with B, and the comparison with D. And therefore, C is the Condorcet winner. Now that's perfectly according to the rules. However, it's sort of interesting to note when you look at the preference schedule that C didn't get any first choice votes at all. It seems that C was the consensus candidate, that is to say the one that was acceptable to everybody if they couldn't have their first choice. This is the kind of result that you might get out of a pairwise comparison. And now let's look also at this example. Here's an example in which there are just 3 candidates called A, B, and C. And let's do all the head-to-head comparisons. There aren't very many to do here. If there are 3 candidates, you only need to do 3 head-to-head comparisons. We're going to do this again. All right, so let's do those three comparisons. Let's first do A versus B. So if we look at A versus B, we see that 25 times A is preferred to B, and only 12 times is B preferred to A. So A wins that head-to-head comparison, 25 to 12. If we look at A versus C, we see that A is preferred 15 times, and C is preferred the remaining 22 times. And if we look at B versus C, we see that B is preferred 27 times, and C is preferred 10 times. All right, so what happened? A was preferred to B. A won that head-to-head comparison. But C was preferred to A. C won that head-to-head comparison. And finally, B was preferred to C. So let's make our little graph there. Let's put A here. And over here, B. And then below I will put C. Okay? And there are three head-to-head comparisons that we made. How did it come out? Well, A was preferred over B, so I'm going to draw the arrow from A to B, pointing towards A. When we compared A and C, C was preferred, so I want to draw the arrow headed towards C. And finally, when we compared B and C, B was preferred to C. Now look at that. If you follow those arrows around, you can keep going round and round and round, always in the same direction. You see B is preferred to C, A is preferred to B, and C is preferred to A. Each one of them has one head-to-head comparison. We see here a lack of transitivity. Now, there's no individual voter that could express this preference. It's impossible to prefer A to B and then prefer B to C and also prefer C to A. But collectively, this can happen. This is an example of what's called the Condorcet paradox.